Welcome everybody for the afternoon session of the analysis and operator algebras section. It is for me a real pleasure to introduce you the first speaker today, which is Ciprian Demeter. I guess you grew up in Romania, right? And he got his degree with Rosenblatt in 2004 in University of Indiana, and he's right now a professor at Indiana University at Bloomington. So the title of his talk will be Decouplings and Applications. So please, Cyprian.
All right, so thank you, Luis, for the introduction. Can you hear me? I'd like to start by thanking to my many wonderful teachers and to the many wonderful collaborators that I had, which essentially have brought me here. So in terms of the overall plan for the talk, I want to think about it as being divided in roughly 4 parts. I will start by giving you some motivation and introduce exponential sums. Then I'm going to introduce decoupling as an abstract Fourier analytic tool. I'm going to show that decouplings do imply most of the times sharp estimates on exponential sums. And at the end of the talk, I'm going to advertise a few examples. There's still something wrong, I think, with this. Still doesn't work. Oh, okay. So here's the general setup. Well, I'll try that also. So we're going to have a collection of frequency points that I'm going to call big lambda. Everything happens in Rn. I will insist that the points sit on a curved manifold, which is also compact, has diameter about 1. So we're excluding hyperplanes, lines, but good examples are the sphere, the truncated paraboloid. Notice that I'm truncating it around the origin. An example of a nice curve is the moment curve. This actually showed up very briefly on the 2nd or 3rd page of Kosher-Birkar's talk just about an hour ago or so. He was talking about the curve of the complex plane. In this case, everything is real. And of course, if n is 2, the 2 manifolds coincide. We're going to be talking about the parabola, which will show up quite a lot in this talk. All right, so I consider a finite collection of points. And the question that I'm going to be investigating is the following. First of all, I want to set up some notation. E of z is going to stand for e to the power 2 pi I z. Z is a real number. And let's say that I take a bunch of complex coefficients. I have a bunch of frequencies, as I said, in Rn on the manifold. And then I want to look at this exponential sum. And given a spatial ball B sub r, this is an arbitrary ball of diameter roughly r, or maybe a cube of side length roughly r, I would like to estimate the LP moment on that spatial ball. Okay? So why is this question complicated? Well, first of all, it's not very complicated if the radius is roughly 1. That is because the x's, the frequencies, don't change too much. They live on a compact manifold of diameter roughly 1. And if x doesn't change much, if x is localized within a ball of radius roughly 1, you can think about this as being essentially constant. It's an easy exercise. But as the ball gets larger, things get more complicated. What I'm showing here are the level curves for 2 such exponentials in the plane. And of course, all these level curves are lines perpendicular to xc1 or xc2. And depending on how these waves interact, they can give rise to either constructive or destructive interferences. You can imagine the maximums of the waves adding up or canceling each other. And this might vary a lot depending on the spatial region. So this all lives inside the ball of radius r. And if you add another exponential, if you add a zillion more exponentials, things can easily get very complicated. Okay, so it's a complicated problem. How do you approach this problem. So first of all, I'd like to understand what kind of radius does it make to consider. Okay, radius 1 is roughly easy. I'll look at points which are delta separated, right? They sit on the manifold and they have some sort of a separation. It's not uniform separation, it's at least delta separation. However, I will not insist for these points to belong to a lattice, so they don't have any rigid structure. What kind of radius am I looking for? Well, these exponential sums, while they are not in general periodic, they are almost periodic. Okay, so you can approximate periodicity by some sort of an almost periodicity in a pointwise fashion. Well, that turns out to be too weak for our purposes. If you know what the classical definition of almost periodicity is, I mean, that's sort of weak enough. I want to look at some sort of radius that captures almost periodicity in an average sense and in a rather sharp way. And there is a simple computation that I'm going to give you here, which shows that actually for hypersurfaces in Rn, this radius is roughly delta to minus 2. We're all looking at the smallest radius. And for curves, it depends on the dimension. It's of the order of delta to minus n. So the computation is obviously for the parabola, which is in both classes of manifolds. And if you look at the points k over n, k squared over n, I argue that it's precisely n squared that you need in terms of the size of the special domain to account for, well, in this case, these are periodic. To account for this periodicity, if you make a change of variables, it doesn't really matter that you integrate over this particular square that starts at the origin. You could move this square around, and n squared here is needed essentially in a sort of naive fashion because of this n squared here. Okay, and you can play this game even in your head for the moment curve in higher dimensions and so on. Okay, so for hypersurfaces is going to be delta to minus 2, for curves delta to minus n. Now things are all sort of nice and beautiful in the periodic case, even though I still have to decide how I estimate this quantity here, right? It is an exponential sum on the torus, but it's still non-trivial. What should we expect? Well, before I tell you what we should expect, let me give you some motivation. Why would we be looking at this kind of exponential sums? You can generalize the parabola in two ways, as I hinted about earlier. You can go to the higher dimensional parabolid or to the moment curve. Let's have a look here, to the first case. So if you choose these lattice points, essentially it's a rescaled lattice that you have here. If you choose these lattice points on the parabolid, if you put some arbitrary coefficients ak, then you end up with the so-called Strichert's estimates for the Schrödinger equation in the periodic setting. So the Schrödinger equation is central in mathematics. Strichert's estimates are one of the tools that help us investigate the behavior of the solution. Jean has started the investigation of this problem back in 1993. His paper got a lot of attention. He solved only the case of the parabola and the parabolid. The higher dimensions remained open. People tried to apply all sorts of number theoretical methods. It has a little bit of number theoretical flavor if you look at it. Well, we ended up solving this problem using decouplings and using essentially no number theory. I'm going to get back to that in the end. On the other hand, if you look at frequency points of this sort on the moment curve, and again, if you integrate on the correct ball, which in this case is, has size roughly n to the power n, then understanding this otherwise simple looking object amounts to solving the Vinogradov mean value theorem, the main conjecture. And this has been a long-standing problem, and again, we managed to solve it for all values of little n using decouplings. So there are applications and motivation coming from both number theory and PDEs. What should we expect when we have such an exponential sum, with separated frequencies living on a curved manifold? Well, we should expect the existence of a critical exponent and of a range between 2 and this critical exponent. And this depends on the manifold, on the curvature, and so on, such that in that range, if you look at the average LP moment of any such exponential sum, on balls of the correct radius, not necessarily centered at the origin, well, you expect that quantity to be roughly of the order of the little L2 norm of the sequence. And we allow R to the epsilon losses. These are losses that sometimes there is hope to be removed, or there are reasons to believe that they could be removed. However, you know, our technology is a bit lossy because of the various induction on scales. I mean, we always pay at least logarithmic prices in these inequalities, right? So this is some sort of an almost periodicity. If you want, you give me any ball, I can move it around, I estimate the LP norm, and I get roughly the same value, okay? You can also see this as being some sort of a reverse Hölder's inequality. Actually, this first inequality is trivial. It's just the usual Hölder inequality, because P is greater than 2. And it's this inequality that we are after when we prove decouplings. The estimate, as I said, is trivial when P is 2. It gets harder as you approach the critical exponent. And if you can prove it for the critical exponent, you prove it for the whole range by just interpolating. Okay?
Like a generalized Khinchin inequality.
Yeah, I mean, you can see it as a form of, I think I say it here somewhere, a square root cancellation. There's all sorts of, there's a hierarchy of how strong the square root cancellation is. I'm not going to talk about the hardest here, but you can view it as some sort of deterministic form of hinching. These are all deterministic coefficients. We're talking about this happening for all coefficients xc, right? So to approach these questions, and there's many such questions, I'm going to propose this Fourier analytic tool called decoupling, and to put it in a more abstract framework, actually I'm going to talk about Banach spaces for, I guess, 2 slides. So let's imagine now that we are in a Banach space, and let's imagine we have arbitrary elements f1 through fj, fn, and I'm trying to understand the norm of the sum. Well, the best thing I can say in this generality is that it's dominated by the sum of the norms of the elements, right? There's nothing better that I can say. Now, here's a simple exercise. If I combine this with Cauchy-Schwarz, I can dominate the norm of the sum with the little L2 norm of the x norms of the components. And then there is this annoying factor that is inevitable to this computation. And in fact, n to the power 1/2 is sharp. It's a simple exercise. Just take x equals L1, functions with equal L1 norms, let's say positive, and then everything adds up to an equality. Okay? So in a Banach space, that's the best we can do. N to the power 1/2, that's the end of the story. Of course, we are interested in situations when n to the 1/2 is not there, or maybe it's replaced with n to the power epsilon for arbitrarily small epsilon. And this is indeed the case if X has extra structure, if it's a Hilbert space, and if all these elements are pairwise orthogonal, then you get something beautiful. This is in fact an equality, but this is irrelevant for the work that I'm about to describe. I'm interested in the fact that this is an inequality. And notice that there is no n dependence here in front of that L2 sum. How do you encounter this situation in Fourier analysis where I work? Well, imagine you work on L2, which is a beautiful Hilbert space. It's L2 over n. And all the functions, how do you make them pairwise orthogonal? Well, for example, you can assume that they are spectral pairwise disjoint. And because of the Plancherel formula, their inner product is always 0. Good. L2 is well understood, but lots of the questions about exponential sums, if not all of them, are interesting in LP spaces where P is greater than 2. So it makes sense to look at LP. If P is not 2, LP is very far from being a Hilbert space. And so you lose this beautiful sort of abstract structure. And you need to, nevertheless, understand what happens to the Fourier transform of functions with you know, some restrictions on the spectra. Now, let me set the stage for decouplings. I'm going to work on manifolds which are nice in the sense that they are the graphs of smooth functions. They can be d-dimensional. They always live in Rn. Here's the definition. Here are some examples. I've already mentioned the parabolid. These are the hemispheres. Then you have the truncated cone. And notice that I cut it away from the singularity, away from the origin, also away from infinity. And also mentioned the moment curve. And at the end of the talk, if I have time, I'm going to mention also other more exotic examples. All right, so you fix such a manifold. And what do you do to the manifold? You partition it. So if you give me a delta, I'm going to partition M into sets of size roughly delta. I put size between quotation marks because size depends a little bit on the manifold. I can tell you that if the manifold is, you know, has non-zero Gaussian, if it's a hypersurface with non-zero Gaussian curvature, such as the hyperbolic or elliptic parabolid or the sphere and so on, then you can really partition it into caps of size or, you know, cube-like, you know, regions of size roughly delta. And the exact geometry is not important. They could be roughly looking like cubes. If it's a cone, on the other hand, it has zero curvature in one direction. And these subsets theta have to have length roughly 1 in the zero curvature direction, and then angular opening, if you want, roughly delta. So let's be a little bit vague for now. And once I have this partition, I can also partition any function whose Fourier transform is supported on the manifold as follows. So what are the p thetas? They are projections. So if you fix a set, it doesn't have to live on the manifold. It could be a subset of Rn. You can restrict the Fourier transform of the function to that set, and then Fourier invert back. Of course, if theta is everything, is Rn, then P sub Rn of f is just the identity. In general, what this operator does is it picks the relevant part of the spectrum and discards everything else. Since this is a partition of M, obviously you have such a decomposition. So it makes sense to look at the LP norm on Rn of such a quantity. So our Banach space now is LP of Rn. And the decoupling problem for manifolds, I could phrase it in the simplest form as follows. If you give me M, and if you give me the partition, the task is to identify the range, the critical exponent in particular, PC, such that whenever you have a function with Fourier transform supported on the manifold, you have this decoupling. So notice that again I have the little L2 norm replacing the more trivial little L1 norm, right? So I replace the triangle inequality with something much stronger at the expense of, you know, localizing things on spatial balls of diameter r and losing r to the epsilon, but for arbitrarily small epsilon. Any questions for now? Okay, please stop me if you have any questions. So this is the question. And I should say that behind this problem, there's also oftentimes the problem of identifying the correct partition. If you give me the manifold, how do I find the correct partition? Maybe sometimes there's more than one, I mean, there's two different, completely different partitions. Well, they could lead to different decouplings, to different ranges, and, you know, but this is a little bit more complicated. I don't want to get into that. Now, why do we care about decouplings, right? Eventually, I'm going to get to exponential sums. Well, decouplings will lead to exponential sum estimates because of the following rather simple observation. You need not know what the Fourier transform of a function is. You'll just have to believe this computation, which you can do in your head, well, if you know the formula of the Fourier transform. If you look at the Dirac delta distribution, and this is not a function, but, you know, it could be approximated with functions that are mostly 0 and mostly 1 near a certain point eta. So if you look at this Dirac delta distribution, if you apply the Fourier transform formula, well, you get an exponential. So something very concentrated on the frequency side ends up being spread all over the place, you know, in a rather periodic fashion. And now let's do this exercise. I have the manifold, I have the partition into the caps theta of size roughly delta. And then for every theta, I pick a point called xi theta. And I can pick that point as I wish. All I have to make sure is that for every element of the partition, I only have 1 point, or roughly 1 point. But otherwise, it doesn't have to be the center. It doesn't have to live on a lattice. I mean, it can be any point. And of course, these points will be separated by roughly delta because of my assumption. All right, so let's believe this computation. And then this gets me to Bourgain's extremely simple but extremely powerful observation from 2013. And it says the following. Let's say you have a manifold for which you have a partition, and for every element in the partition, you also pick 1 point that you call xi theta. Also, let's assume that you have arbitrary coefficients, and let's assume that for this configuration, you want to prove the reverse Hölder inequality. So again, this is more like the L2 average L2 norm. This is an average LP norm. How are you going to do that? Well, prove a decoupling. Prove a more general statement for the same partition, for the same manifold, right? And notice that I'm allowing an R to the epsilon loss on both sides. And how are you going to get from here to here? Well, if you want to cheat a little bit, you just plug in a function whose Fourier transform is this combination of Dirac deltas. Because again, what this tells you about the function is that f itself is the sum of these, is this weighted sum of waves, which means it's exactly that. Okay, so if you plug that into here, and if you do it rigorously with approximating the Dirac deltas with smooth functions, it's a 4-line exercise to actually show that this immediately implies that. So this is a consequence of decouplings. So now you're left with proving the decoupling for that manifold. Okay? So this is the game. Bourgain made this observation, and while again it's easy to read it and believe it, I mean, it's very surprising. You say, wow, really? I mean, this looks very discrete, and I mean, can something like this really hold true? Well, the answer is it does. So let me see what I have on the next slide. There's some negative energy in this room that prevents... All right. So this is the slide that I want. The first decoupling was proved by Tom Wolfe in 2000. And he essentially came up with this technology and proposed this technology and argued that you can do lots of things with it. He looked at the cone in 3 dimensions. He didn't prove the estimate for the whole range, but he has already done something remarkable. In particular, he connected this highly oscillatory problem. Whenever you have something involving the Fourier transform, things oscillate a lot. He connected it with things from incidence geometry. So very briefly, incidence geometry is concerned with the number of intersections between 2 different structures. For example, you could have points and lines in the plane, and the beautiful Semerey-de-Trotter theorem says that there's only that many incidences, that is pairs of points and lines that intersect, in terms of the number of lines and the number of points. There is a similar problem involving circles. In this case, it's just one family of objects, the circles themselves. And you could ask lots of questions. For example, if you assume that no 3 circles are mutually tangent, I mean, not just mutually tangent, but tangent actually at the same point. If you exclude this silly example, in how many ways or how many pairs of circles can be mutually tangent? So I'm showing you here simple configuration. I drew this by hand using some of the tools of my 9-year-old daughter, and somehow I managed to make them all tangent, at least from afar. So in this case, any 2 circles are tangent, but it gets harder. As you add more circles, it gets harder, right? So it's a striking connection between this and something very oscillatory. However, his proof showed that there is such a connection, and this is one of the themes that followed us through the forthcoming developments. So I should say that Tom Wolfe, I mean, perhaps the main reason he invented decouplings is because he cared about local smoothing for the wave equation. In short, this says that if you look at the solution for the wave equation, linear wave equation, the solution at any given time has some sort of a regularity, but if you average the solution over compact times, then you gain some regularity. Unfortunately, the interest in this problem died around the same time when Tom Wolfe died. He died around the same time, maybe 2001, in a tragic car accident. And people looked at it to some extent, but it was really Jean Bourgain which took the problem at the next level. So in 2013, he proved a decoupling for the paraboloid this time in an incomplete range. And he introduced a new tool, which also has to do with incidence geometry. And this new tool is the so-called multilinear Kakeya inequality. So let me briefly tell you about the Kakeya problem. I'd be surprised if there's anybody in this audience which doesn't know about that, but it's always fun to say a few words about it. So a Kakeya set in Rn is a set which contains a unit line segment in every direction. And the silly example is a disk of radius 1, at least one in R2. Of course, if you look at all the radii, they cover all the directions. What's interesting is that there are Kakeya sets with 0 Lebesgue measure. So they are invisible to the naked eye. And the conjecture is that they still should be big in some sense. They should have full Hausdorff dimension. This conjecture is open in 3 dimensions and higher. It's only solved in 2 dimensions. You can reformulate this Kakeya conjecture, your slight version of it, by using cylinders of length roughly 1 and opening delta, or rescaled versions of them. And it becomes a question about how these cylinders pointing in all sorts of directions in Rn intersect with each other. It's about an LP norm of the characteristic function of this family of cylinders. Interestingly enough, there is a multilinear version of this question, which I have on the next slide, which has been solved. And this is the theorem due to Bennett, Carberry, and Tao, so it's relatively recent. Let me read it rather quickly for you. So we have in Rn, we have n families of tubes. This time I scale them like this, so you can think about my hand, length about r, it's a cylinder, the radius about square root of r. And in each family, so let's say in this family, I insist that all the tubes point not in the same direction, but in nearby directions, close to the unit vector. And then I have another family of tubes, and again, they don't have to be parallel, but they more or less have to point in, let's say, that direction, and then you choose a family for each of the unit vectors. Then you give yourself some positive coefficients, you cook up the weighted characteristic function, and you try to understand the geometric average of these functions. It turns out that the correct LP space to investigate is n over n minus 1. This is the average over the ball. Let's assume that the tubes or cylinders leave inside the ball of radius roughly 4r. And this inequality quantifies the intersection of tubes from all directions by essentially showing that these functions are somewhat independent. What you recognize here is some sort of a geometric average of the averages of each individual function, and then of course you get back to the original LP space. This is an incidence geometry problem. There is a discrete version of this, the joint problem. If you have a bunch of lines in, let's say, R3, you can imagine how many joints you have. A joint is a point where 3 lines that span R3, right? So how many such joints do you have? And this was a problem that was solved only recently. And this is, the sort of thick version of that involves tubes. So Jean managed to put this theorem to work. He didn't need any circle tangencies. And then in 2014, just a little bit after that, I picked up interest, I joined forces, and we managed to prove the sharp decoupling for the paraboloid in all dimensions. The critical exponent in this case is 2 times n plus 1 over n minus 1. So how do we do it? The methods are very similar to what Jean has used, with one new ingredient. So in particular, we use wave packet decompositions. which leads to tubes and the multilinear Kakeya inequality. We combine it with a very simple tool called L to orthogonality. So at the end of the day, we get from L to orthogonality to LP orthogonality, if you want, in some broad sense. We also use the equivalence between multilinear and linear decouplings. This has been another recent development, sort of 8 years ago or so, due to the work of Jean and Larry Guth. And the new ingredient is some bootstrapping argument, some sort of a ping pong between linear and multilinear decouplings, which takes advantage of many scales. So in my field, whenever you have a spatial ball of radius r, there's two, in most problems, there's two scales that are important, scale r and scale square root of r. And this is accounted by curvature. In our case, we still give importance or significance to the scale square root of r. It's just that we have to play with more such steps. So one of the surprises that came around the same time, so after we solved the parabolid, we also realized that we can use the result for the parabolid as a black box to actually answer Tom Wolf's original question. He was interested in the cone. And we managed to prove the sharp decoupling for the cone in all dimensions using just a slicing argument. So if you think about the cone, and if you slice it the correct way, you can see the cone as being a stack of parabolas, right? Or paraboloids in higher dimensions. If you do it correctly, then you can prove that. So at the end of the day, we didn't need the circle tangencies. Our argument is a bit easier than Tom Wolf's. However, at its core, we'll still have incidence geometry in the form of the multilinear Kakeya problem. Any questions? Okay. So in 2015, Larry Guth has joined forces with us, and together we completed the decoupling theory for the moment curve also. You'd think that curves are easier than the hypersurfaces. I mean, they're certainly at the other spectrum in terms of dimension. However, they are more complicated. The restriction theory of curves is easier than the restriction theory of hypersurfaces, but for decouplings is the other way around. This is a bit mysterious. How did we do it? We used more or less the same technology with one new ingredient. This time we don't just use the multilinear Kakeya for tubes. We have all sorts of intermediate shapes. We can call them plates. Imagine instead of having cylinders, you have, books maybe, right? Which have two long dimensions and just one thin dimension. Well, this is again an abstract free analytic result. If you prove it, then you get for free the main conjecture in Vinogradov's mean value theorem, which was attempted for a long time, attacked for a long time using number theoretical methods. So I'm not going to assume that you know what the Vinogradov mean value theorem is. And that's why I will give you a slide presentation. It's a fun theorem, very easy to describe. And it is about Diophantine systems of equations. So I'm going to fix three parameters here. Little n is the dimension. Capital N is a truncation parameter. S counts the number, more or less, of variables. So what we have here, you're looking at this number, which represents the number of solutions. These are integral solutions of this system consisting of n equations, right? I equals 1, it's linear, then quadratic, and so on. And you're looking at the solutions x1 through ys, all between 1 and n. There's always a lower bound, a trivial lower bound. I'm going to let you choose the x size as you wish between 1 and there's n to the s ways. And then I'm going to choose the y's essentially by permuting, or maybe not even permuting, the selection that you have made. Right? So I have at least n to the s trivial solutions. But the Vinogradov mean value theorem says that if you look at the correct value of s, which is n times n plus 1 over 2, then there can't be new solutions. Well, apart from n to the epsilon, right? So the new solutions only account for, you know, more or less the same proportion compared to the trivial solutions. Here's two examples. In 2 dimensions, we end up with something that has been known for quite a while. The critical exponent is 3 here. The system reads as follows. It has been known that this doesn't have too many non-trivial solutions. One way to prove that, rather elementarily, is you can manipulate the system and reduce the problem to the question of representations of an integer as the sum of 2 squares. And we know there's not too many ways of doing that. And this is one example where some epsilon here is needed, at least some logarithmic factor. However, the case n equals 3 has only been solved recently by Trevor Woolley using a sequence of improvements of his method, efficient congressing. This is a method that relies on number theory, at least superficially, or at least you know, when you read it for the first time. And the system looks like this, so it's more complicated because it has the cubic powers. Nevertheless, he was able to prove the sharp result. And as I hinted about earlier, at the end of 2015, the paper has appeared in 2016. We managed to prove the theorem in all dimensions. And Trevor was able to refine his methods soon after that to reprove this result. Why is it that we could solve this problem? Well, it's because the number of solutions has an analytic representation. If you just use the orthogonality of the exponential sums, you can rewrite this number of solutions as an integral over the torus. So you're in the periodic case, and then you choose the right exponent because you have 2 as variables, and that's it. So once you prove the correct decoupling, the bound for the exponential sums is rather immediate using Bourgain's you know, conversion mechanism. Now let me say a few words on the philosophical side. Our proofs of the decoupling theorems rely solely on Fourier analysis and a little bit of incidence geometry. In particular, they do not require any number theoretical input. We cannot solve all the problems, but in the problems that we can solve, in our proofs, the rigid algebraic structure of the integers is meaningless. The only thing that we use about the integers when we count solutions is the fact that this guy, I mean, consecutive integers are separated by at least 1 over 10,000, or you can put any number. So you have at least some separation between them, but the algebraic structure is meaningless to us. So in light of this, it makes sense to sort of conclude that things like the Vinogradov mean value theorem truly belongs to analysis, not to number theory, even though it was sought after for about a century or so using mostly number theoretical methods. I should also say that one of the pleasing aspects of decouplings is that we can not only decouple point masses, right? I mean, this is where the spectrum of exponential sums is supported. Well, we can decouple whole arcs. We can decouple functions whose Fourier transform is spread over the whole manifold. And this is useful in harmonic analysis in PDEs. There's more and more applications coming every month. Let me go briefly over some of the examples, summarizing also some of the things that I said earlier. We now understand the decoupling theory in a sharp way for all hypersurfaces with non-zero Gaussian curvature. There's lots of applications. Perhaps most of the applications are here. 3 Hertz estimates. We can improve the moments for eigenfunctions of the Laplacian on the torus. This is part of a bigger problem. We can address somewhat successfully this manifold, the torus. We solved the cone. This has 0 Gaussian curvature. We made progress on the local smoothing conjecture. These applications in complex analysis, Bergman projections. There's even a nice application, recent application by Jean and Watt, some progress on the Gauss circle problem. This is counting the number of lattice points inside circles of radius r. I mentioned the curves with torsion, Vinogradov mean value theorem. And on the more exotic side, well, you can think about any manifold. I mean, any manifold of the type that I described has a decoupling theory that waits to be discovered. It just gets harder with dimension because, you see, for hypersurfaces, you have curvature, the principal curvatures, that for us tell the whole story. For curves, you have torsion. Torsion measures whether a curve is planar or not. But if I give you a 7-dimensional manifold in R24, I mean, the curvature tensor is very complicated. However, Jean did something extremely interesting. He made progress. He still holds, as far as I know, the record on the Lindelof hypothesis. This is about the growth of the Riemann zeta function on the critical line. By using a very simple decoupling, essentially he needs a 2-dimensional surface in R4. And there has been some very recent work. You can generalize the Vinogradov systems to higher orders. And I'm not going to say what that means. This is related to a so-called parcial Vinogradov systems. I've done some work with my former postdoc and with Jean in the cubic case, and we solved the problem. And now Gu with Zhang have essentially solved the whole problem in all dimensions. And this is a tour de force. It's very, very pleasing. I can't resist. I have 2 more minutes. I can't resist advertising some open problems. I told you how much you can do with decouplings, and we continue to be surprised every day and pleased. However, there are some limitations. I'm going to argue that they are not, you know, ultimate limitations. It's just that decoupling needs to be understood better and refined. So in principle, I think this could be attacked using decouplings. I hope you're going to find these problems lovely. Let's say that you have a subset of an abelian group and an index n, and then you can look at the energy of nth order. This counts the 2 n tuples in the set such that this happens. Okay, you've seen this before on the previous slide. So it's a linear equation, right? What can you say about this energy? Well, it's always at least as big as the size of n to the power n, right? Because again, you can choose the first n coordinates and you can duplicate them on the last few, right? The sets for which this lower bound is more or less sharp up to some epsilon losses are interesting sets, okay? And we believe that this should be true for arbitrary subsets of the sphere when you look at the 2 energies. So if you count the additive quadruples on the sphere, you know, you fix the configuration of points, could be ugly, could be very complicated. It should be the case that you don't get more than the size squared. So, in other words, there aren't too many non-trivial additive quadruples on the sphere. This problem served as one of our original motivations when we started working on the decouplings, you know, 5-6 years ago. And interestingly, this problem, I mean, we managed to solve it for the parabolid. If you have the points on the parabolid in 3 dimensions, if you project them down to R2, if you look at their shadows, it turns out that any additive quadruple on the parabolid corresponds to a rectangle downstairs. So every additive quadruple gives rise to right angles. And then the question is, if I give you n points in the plane, what's the maximum number of right angles that you can find in that set? There's a beautiful theorem of Pach and Sharir, which uses the Semeret-de-Trotter theorem, which says that there's the most n squared log n. And this is a sharp result. So in that case, it's easy. For the sphere, it has too many symmetries. You think they are related. They should be. They have the same, more or less, type of curvature. This is still open. Lots of people thought about it. I'm looking for somebody which proves it. Similarly, for the circle or the parabola, the question is about E3. So you look at 6 tuples. Again, prove that this is the case. You know, Jean and Bombieri have used a lot of algebraic geometry and algebraic number theory, I should say, to prove this conjecture for very particular subsets of Z2 intersected with a rescaled version of the circle. The best known bound, if you use just traditional methods, is Semeredi-Trotter. If you assume the unit distance conjecture, now the beautiful conjecture from incidence geometry, you do get the right size, but I think this problem should be a bit easier. Now, why do I mention these problems? Because if you make the additional assumption that the points on the circle or on the sphere are also separated, if they don't clump together too much, and you can quantify that, then these things follow from our, I mean, the correct bounds follow from our decouplings. The question is, or the next step would be, the next generation of decoupling theorems might be about decoupling not into sets of size roughly delta, but into arbitrary sets. And I'm not going to get into that, but I hope, again, that somebody's going to get interested in these otherwise easy-looking problems, and I'm looking forward to seeing progress. Thank you very much.
You mentioned that this critical number P, it somehow depends on geometry and the manifold. Could you add several comments? What is important?
It does depend in some way on the curvature, but for example, it's the same for the sphere and the paraboloid. So it doesn't depend in a superfine way. I mean, the sphere has constant curvature. The paraboloid is only sort of positively curved, but no constant curvature. It doesn't care about that. Actually, the way we prove a decoupling, let's say, for the sphere is by approximating it with paraboloids, using Taylor's formula and some sort of induction on scales. It's very hard to read this critical exponent from just the dimensionality of the manifold, right? It's a number that pops out through computations. There are some standard examples that you test, and at the end of the day, you end up with a number. So whether there's something deeper than that, I can't tell you.
So, any other question or comment? Okay, if not, let's thank the speaker again.